Okay, I think this is all working. Oh, wait, no. Private, okay. Okay, is this streaming? Yep, okay, great. So I'm just going to, now that I've got this live, I'm just going to switch it over to just like a terminal view while I, tweet out announcements and stuff. I'm sure in future I'll have this more smooth. But yeah, as I said in the last couple of days, I've just had a bit of difficulties getting this set up. So yeah, cool. All right. Yep. Okay. All right. First of all, can people hear me? All right, we've got one person on. I guess I need to get used to just going with this rather than viewing it as sort of a room that I'm presenting to, just sort of going about the work and talking about things. So yeah, I'll dive into stuff. All right. So what I'm interested in going through today, and a thing that I've been thinking about for a while, is what would it look like if we rebuilt spaCy more on PyTorch. So this has been particularly relevant over the last couple of weeks. So the last couple of weeks have really put my focus much more on it because I've had so many problems building our linear algebra stack, which is this sort of low-level details that we draw in because we have our own machine learning stack. And that's seeming less and less viable or less and less attractive these days. The other thing is that, the decision around how spaCy does its ML and how that actually interacts with the pipeline goes back to decisions that were made, 10 years ago. So I think it's good actually to let's go back to like, you know, let's see, where's tag 1? So yeah, I don't know, v 1.9.0, I think it should be fine. So like v 1.9.0. All right, so when was this? So this was 2017. So I think this is still plenty old enough. So yeah, let me just look at how we had this this all. It's actually kind of interesting to go back this far. So I'm particularly interested in how the machine learning worked at this time. So if we look at, say, the tagger, okay, so this is, so that's not a thing there. Tagger, yeah, okay. So let's look at the tagger here. So the tagger, when in the first versions of spaCy and the parser and things as well, didn't use neural networks. When I started writing the library in 2014, this was just at the verge of when neural networks started to be competitive, and on the tasks like, you know, parsing and part-of-speech tagging and things, they were still behind the performance that you got from linear models, and you know, especially in speed. So they were getting similar-ish accuracy, but with a lot of effort and you know, a lot of and slower. And at the time, my take on this was that there had been waves of different ML technologies in NLP that got to this level of about the same performance, because the corpora and the problems were such that there were many different ways to solve the task, many different ways to access the basic information that you needed around the surrounding words. And you could structure that with a wide variety of machine learning models. So what tended to happen is there would be this effect of, you know, all the smart people flocking to some ML approach that seemed new. And that investment of energy and effort yielded results that were maybe fractionally better than the previous ones, but and especially fractionally better if you didn't combine them with other techniques that gave to truly state-of-the-art performance. And so we ended up with these waves of successive things like spectral models and you know, different approaches like this that seemed very promising and that weren't actually going to be fruitful. So I decided to hang back, and I built spaCy to weight it on methods that were currently best. So what we actually do here is for the tagger and for other things, we define a set of features, and what this enum is the feature codes. So P2 means the previous word, and then these are the actual features that we go and say. So we're going to have a numeric indicator that refers to like the word form of the second word previous, the cluster of the second word previous, the shape of the second word previous, the prefix of the second word prefix, the suffix, the part of speech, the lemma, and then these flags, which indicate you know, things like whether it's capitalized and that sort of stuff. And then you've got the same thing for the previous word, the current word, the next word, and the word after that. And so in order to actually do the predictions, what we do is we have this function set features. So we're filling in an array that we do with this, and then let's see, and then this is just an instance of this average perceptron class. So this is a class that's defined in Thinc, and what all that this does is during training, it's going to iterate over the examples, and if it got the example wrong, it's going to decrease a weight for each of these. It's going to -1 to weight for all of these features that were seen on the example. And if it got the example right, it'll do nothing. So this means that you end up changing the weights in the examples that you got wrong. And this is enough that if you iterate over this and then you average the weights afterwards, you get performance that's good as other models, at least on tasks like this. And so it's extremely simple to code, it's extremely fast to train, and it's very easy to reason about. So this is how I did ML in the first versions of spaCy, and that like pragmatism of it was a big draw card from it. So if you're doing machine learning this sort of way, it explains a lot of how the machine learning was structured in spaCy to start with. So for a start, you're going to have update methods that are on each of these components, because there's no sense in having some update function that would be sort of global or external or something. There's also not really a sense of a separate optimizer, because there is kind of no optimization algorithm here. It's the optimization algorithm of the average perceptron is kind of built into the algorithm itself, because all you're going to do is just look at the examples you got wrong and do this -1 thing. So there aren't these separate steps of saying computer gradient and then optimize the gradients with some solver like stochastic gradient descent or Atom or something like this. So these weren't separate steps at the start of spaCy. And so after this, before too long, at the sort of V2 level, this is when I switched over to the neural networks. And this took a bunch of research to do to get models which, were performing well, but I kept the same sort of structure of having the components all have these update methods and the language have its update method. So let's go back to the present and I'll show you what this looks like. All right. So let's actually start with the training loop. So the CLI train. So what happens when you call spaCy train? Like, how does this actually work? Well, we've got it all happens within this config, and this CLI part is only an outer shell. We try to keep the logic separate. So all of the fun stuff lives in this training.loop place. So all right, let's go here to training.loop. So here we have train. So here again, we've got our NLP object. We've got the path that we're going to save the model into, and then we go through the corpus. We build the training dev corpus using the readers that are the registered functions there. We take the optimizer that's been specified in the config, and then we're going to do this loop, train while improving. And this takes the NLP object, the optimizer, function to create training batches, function to create the evaluation callback, etc. So let's see here. So we call this train while improving, and this is the basic loop. So we're iterating over these steps. The function before create the iterator has divided into batches and told us the epoch with it, and then if we have sub batches divided, then we go over those, and we call this update method on the language class. So, and within that function, so this takes a batch. So our examples, it takes optionally the optimizer. If you don't take the optimizer here, you can call it. It gets called afterwards to clear the gradients, so you don't have to call the optimization on each step necessarily. So this allows the sub-batching idea there. So you can have a gradient step that is essentially over a batch that's larger than you could easily have in memory. So yeah, we're going through here, and to do an update over the batch, we go over the components in the pipeline, and we call all of their update methods. So, and within each of these component update methods, so let's say pipeline, and let's go to the tagger here. So all right, now we're updating the tagger, and what this does is it calls into our library Thinc, and the way that Thinc does updates is you call a forward pass function that's called begin update. This does the forward pass and returns you a callback that you call with the gradient that does the backward pass. So the nice thing about this is it's easy to compose models. There's no special sort of top layer or container of model. If you have some model and then you add something afterwards, well, that's just going to be this combinator that chains them together and manipulates the callbacks. So I always found this kind of elegant, and it's, you know, I find it quite nice to program in, but it does limit the amount of, the way that we can optimize. And, you know, also has the disadvantage that it's not PyTorch, which, you know, obviously a lot of people have worked on PyTorch. PyTorch is very good. So yeah, we call this begin update. We compute our loss, which is, you know, this D tag scores, and then assuming we have our then we backpropagate, and then if we've been passed an optimizer function, then we call finish update, which is actually going to call the part that changes the weights. Okay. And triangle pipe is the parent class here. All right. And yeah, this just called, this is you know, a method on the classes, so that if some pipeline component needs to do something special here, it's able to do it, but otherwise it just delegates it to the model object. All right, so what's the point here? The point is that because the language object has essentially has control of the optimization part, it becomes very difficult to do optimization with in PyTorch or some other library properly. Imagine that we had all of these models were just PyTorch models, and we rewrote the pipeline components to do that, and all of that worked fine. Well, what we would end up with is we still have this sequence where spaCy is trying to iterate over batches and trying to call individual updates to individual components. And this really defeats a lot of the advantage that we should be getting out of something like PyTorch. What we want is to be able to hand over the training of these models to some other abstraction. So, for instance, the modern BERT paper, which came out recently, uses Mosaic. So let me just switch over to that so that we can look at that. I think it's a good this transition. Yeah, transition. Okay, cool. And, yeah. Okay. So yeah, if you, let's say modern BERT GitHub. So let's look at their GitHub. So for people who haven't been following the latest things, essentially this is a yet another take on BERT that actually finally makes good enough, or at least according to the community and the consensus excitement about it. I haven't reviewed it in so much detail myself. There's a general feeling that this is one that's actually worth migrating to as a drop-in replacement to the BERT models that we've been using. And certainly it's not hard to believe that by now we should have something that should be a good enough drop-in replacement to BERT. But I think it's a good example of how you would do training if you're not encumbered by this history of decisions in spaCy to go back even before the transformer models and before GPU computing was so central to linear models that were on CPU, and especially a particularly simple family of linear models. So here we have training heavily leverages the composer framework. Interesting. So let's look at that. So this is this thing in Mosaic, and let's have a look at what they basically want us to do with this. Like, okay, how can we use this in spaCy, or what will we take to use this in spaCy? Well, attractively, you get this training class, right? And you pass in a model, you pass in your training data loader, you pass in the durations, and you pass in the algorithm that you're doing. And the point of this is that it's going to take over
any low-level details about assigning things to GPU or resuming training or making sure that the graph is optimized well. Or, I guess the graph optimization happens at the PyTorch layer, but there's still a lot of things that you would want from a training abstraction that are done more generally, that we should be able to take advantage in spaCy in order to actually utilize GPUs properly, especially at training time. And we're not able to do that because of the way that the training is structured. The way that spaCy's training is structured is interleaved with the language operations. And this means that you can't do something like this because the model is a member of the pipeline components, and the training loop is going to do things to the batches based on the components are based on the tokenization, and then call all of those components separately. So all that we're left with is calling, the update callbacks on individual batches, which means asking PyTorch to compute some gradient or like for some batch, and then asking it to do one update. And so if we just use PyTorch in this way, which is how we use PyTorch with the current wrapping approach in Thinc, we're missing a lot of the advantage. And this is a key reason why it's actually not really possible to get as good performance as especially during training for spaCy as you would for other things. This is masked a little bit because the actual models are very efficient architecturally in spaCy. They're very well sort of fit to the named entity recognition and dependency parsing problems that spaCy solves in its trained pipelines. And so the models are quite small, and that means that they still train and run quite fast. But if you look at like the GPU utilization, it's really low compared to what you would be getting otherwise. And when you try to run them with something like BERT as a pre-process, they're indeed not performing the way that we would like them to perform. So the question is, what will we do about this? Like, how can we get to this sort of training abstraction, or how do we get to use this sort of thing? And how do we get from where we are to there, so that we can actually use PyTorch properly? We can sunset a lot of the this complexity that we're currently having with the current stack, and really build for the future where GPU computation is more and more central. So spaCy until now has been very, we've had it as a key goal to perform well on CPU, and that's been given the library a sort of unique place in the ecosystem, and I still think that that's valuable. But we can get good CPU performance. We can still have good CPU performance, re-architecting things to make good GPU performance possible. And I think that good GPU performance is more and more important if we want to update architectures for the future, so that we can actually use larger models than we're currently using. So if you look at the GPU cards that are coming out, the size of model that you can feasibly run or easily run is getting larger, and there's always going to be some latency attached to making some batch of predictions. So to a certain point, a certain level of size is sort of free, because you'll spend about the same amount of time with a very small model as you would with a larger one, if the time becomes dominated by the latency of making these predictions to the model. So that sort of efficient threshold or efficient model size is getting larger. And in order to actually make use of it and to get the best compromise that we should be getting, we need to migrate to something like PyTorch. Well, actually, there's no point saying something like PyTorch. There's no other candidate. It would be specifically PyTorch. There's no way we're considering something like JAX or, and I think, I haven't had good experiences with TensorFlow. It would definitely be PyTorch. All right, so the question is what to do. I think a nice way to go about this sort of situation is to imagine imagine a sandbox. Like imagine we didn't have what we had. What would we do? Like how would we design this? So in my head, this thought experiment is, I call this like spaCy. So let me do a transition back to the terminal, and then we can, yeah. All right. Okay. So imagine we were making a new library, and we didn't have to worry about backwards compatibility. So we're making a new NLP library. Imagine this. So let's call it spaCy. And you know, we're here. So how would we design such a thing? What would the language class look like? Like what would we retain and what would we not retain? So let's, you know, make our thing here, and we'll go. So for a start, you know, just to be bold with this and to, you know, embrace that we don't have to do things the same way. Well, should we really call it the language class? I've always slightly regretted this this name, and it does have, you know, in our new imagining of things, it will have slightly different responsibilities. So let's call it just pipeline. All right. So we're building a pipeline class. So let's say, you know, class pipeline. So tokenize text into a doc object and apply some sequence of operations. So now, you know, let's have a look at, you know, the spaCy language class and just sort of at a high level view and imagine what sort of operations we would actually have. So let's not worry about initialization to start with. Yeah, so I think we'll probably want something like metadata and stuff. Let's leave the question of the config aside for now. And just look at, you know, the central API around components and stuff. So you know, I think it's clear that we want stuff like, you know, a list of components. So let's, you know, say, yeah, properly def components. And yeah, let's call that. Yeah, let's actually keep it the same way, and we'll say component. And for the purpose of typing, let's all right. So yeah, similarly, you know, we'll imagine that we still want to have some property where we've got the component names. We've got something that, you know, just returns the pipeline. I don't know whether we would call it just this. We've actually, this is the same as components, isn't it? I don't know what's going on here. Wait. So that's all components, and this is the one that's like, you know, currently enabled or something like that. All right. So yeah. Well, you know, active components, something like that. I don't know. Then, yeah, so we've got component names, active components, yeah, pipe names, etc.
All right, let's leave aside this question of the factories, which is another thing that's tied into the config. So the way that spaCy works at the moment, is we want to make sure that when you've got this language object, you're able to rebuild this from some abstract description, and this means that when you add a pipe or you create a pipe, you refer to it by a string name, and the language looks up the factory that produces it with the arguments. So let's keep things simpler than that for now, and assume that we're just going to get our components as built objects for the sake of our sandbox here. I think this is also a reasonable method that we would want. Okay, then let's leave aside all of this config stuff. This is more config stuff. We'll leave aside the analyzing. Clearly we want some way to get the things. Let's assume that we don't necessarily need some way to create the things because we're just getting them. We're not doing that, and then we're adding. So here, this would be something like okay. Oh yeah, sure. Okay. Yes, and we'll still want this sort of signature around the before, after, first, last, etc. That all makes sense. Clearly we want to be able to ask whether it has some pipe. Replacing is also a very reasonable operation. Well, actually, it's not strictly necessary, so let's stay a bit more minimal than that. Same with renaming. Oh, actually, this is kind of important. Remove. And then so there's this stuff around this area. So now we get into the more interesting stuff. So now clearly we want this sort of function, which is call. So we're going to have text. Let's assume that we still want this stuff around disabling pipes. We'll remove this sort of config. So now, what would this actually look like? Class doc. So I think if I was starting again from a sandbox, one thing that I think would actually be kind of nice would be to have pre-processing components owned by the pipeline as well. So these are the operations that apply over the text, and you do those. You make those manipulations to the raw text, and then you run the tokenization afterwards. I think this would be kind of nice or kind of useful. So let's imagine that we're doing it this way. So we have if instance, if not, is instance text off. We have
text equals self.doc. And then, just as before, we're going to have something like component and self.active components. We'll have so now let's just do this slightly differently. All right, so all that we're doing here is applying the pipeline. You'll have some function that's like make doc. As a text, and then we'll return the doc. Okay, so you already see some members that we're supposed to have here. We're supposed to have a tokenizer. We're supposed to have some preprocessors. Maybe a list, and then components of the list as well. Okay, and then this be okay, so let's move forward. What else do we need? What else will we actually want? Yeah, I mean, I do think we'll want this stuff around it, selecting pipes, etc. But let's leave aside this creature comfort. Let's say we don't want this update function. So this is specifically something that we don't want to do. We don't want to have the language object have any control over that part. Instead, that's going to be handled somehow separately. There's going to be some sort of training function that takes an NLP object and some description of how it wants to be trained, and it's going to do the work there. The language class itself is not going to do it. So we're not doing that. Also not doing this rehearse method, which we always thought was a promising idea that never quite finished off. We're not doing this beginning training stuff. Let's imagine that initialization. This is an interesting question whether we actually want to do this now, but let's assume that this as well is handled by as part of the training. I think that actually makes sense. Same with resume training. This part is definitely worthwhile. Being able to set an error handler that means that as you're processing within pipe, within NLP pipe, if you have some you're running this over millions of documents, you want it to just continue on the errors, and this can't be easily done in a generator approach. So that's why we have this. And I think it would be a feature that would be important, even in this sort of sandbox thing. So return and by the way, the reason why, there's all of these sort of extra features which, you could strip back for the purposes of having this sort of sandboxed approach. I think it's worth, like one of the ways that I do this when I'm doing this sort of thing is actually to include some of these extra features than the ones which I think are strictly necessary, because you always get surprised by the interaction of requirements that you have as soon as you start needing these bells and whistles. Then it's very easy to find that the way that you've structured something doesn't work so well or is inconvenient with this. So stuff like adding an error handler it's easy to say, well, look, that's just, some detail. Let's like, stay more focused on the bigger picture. I think at least some of these requirements, it's good to sort of pencil in, and so that we're already thinking about, like, okay, if you're redesigning something, make sure that you don't end up missing some of these requirements in the redesign without having some exhaustive, like, design document or something like that. So evaluation, this is definitely another responsibility that I'd like to take away from the language class. This always worked kind of awkwardly. There's no reason why something else can't do this. And the specification of like scoring and stuff in each of the components is quite awkward. So, there's many ways that you could evaluate some output, and it's awkward for the components to sort of know that. And it runs into the problem that you have with object-oriented design of having these like m times n operations. So if, in theory, the evaluations that you could do over, say, a text classifier are one set of operations, and the algorithms that you can solve text classification with are, another set of operations. Having a class that does both means that you need you have the product of those classes. And you can try to solve some of this with inheritance, but it's awkward. And so it's, where possible, it's better to sort of take these things away. And if we can have some scorer that operates over the components of different types, so that they don't express an opinion over the scoring and they don't have like evaluation functions and that sort of stuff, then that's good. The flip side to this is if somebody, let's say somebody, comes along, they develop a component. How do they do all of the things? How do they make it support scoring? How do they make the scorer supported? How do they make the training supported? That sort of stuff, if it needs something different from otherwise. And that's where you end up with these sort of entry pointing mechanisms and that sort of stuff, which have their own disadvantages. So the extensibility in some ways is sort of flatter or like, simpler when you put everything together like that. But there's also disadvantages in how you do it, because you get classes that are doing like, multiple things. And I think certainly, even if you went back on the evaluation, the training, I think, is a clear problem. And so that's one which, we need to, I'm interested in designs which take that away. So similarly, create optimizer, not something that the language will be doing. Use params. This is an interesting one as well. There's this context manager that really only gets used as part of the training process, because we have this step of using the weight averages, where we can have this context manager where you load in some parameters and then restore to other parameters afterwards. So this is, I think, let's imagine that we don't have that sort of requirement. Now this pipe function. If I were doing this again, this would definitely be simpler than it is now. The two things that I've long hated about this are, one, the multi-processing. I always regretted adding that, even though it is convenient in many ways, just because the complexity that we take on from that is just so much more than having the multi-processing happen outside of spaCy at a higher level. And the other one is this issue of having this as tuples flag, where you can pass in an iterable of something like this. So you can pass in something like x my JSON blah blah blah, and then you call nlp.pipe, and what you get out of it is doc, and then my JSON, etc. And where the other part of the tuple is a completely arbitrary object. So this is nice in many ways because let's say you want to parse something like, you've got these JSON objects and they've got a text field and you want to parse that text field, but you need to associate the resulting doc back to the text. If you didn't have this sort of thing, you would have to you'd have to jump through some hoops to get this, because you can do something with like itertools.t, which is actually how the implementation works, or you can keep a buffer yourself and then associate it back with indices and stuff. It's all quite awkward. The problem is that this happens at the same method as the pipe method. So this sort of like flag, which changes the mode, debated this back and forth at the time, and I was very conscious of the disadvantages of this, and yet I still went this way, and I've regretted it. That said, maybe if I took the other fork, then I'd say, having this second method is like really annoying as well. But I want to go to path which we don't know sucks at the moment, or like maybe we underestimate how much it sucks because we've seen how much this one sucks. So we're going to keep the pipe simple here, and we're going to say texts. We'll still make this a union of stir or doc objects. I think the opportunity to produce doc objects outside of the pipeline and pass those in, I think, is actually pretty important, and it makes a lot of things easier if you have some extra processing and things that you want to do and you don't want to keep it in the pipeline. It becomes the easiest way to solve certain problems. Because you can pass in a doc into the pipeline, if you have, say, two spaCy pipelines and you want to run them separately, you can do that. You can have one pipeline that produces the docs, and then another pipeline, another NLP object, has extra steps that are done, and it doesn't need to tokenize it. So I think that's a nice feature, and I would still support that in this imaginary sandbox redesign. Here we'll also want to take the batch size customization. So we go batch size, and we're not going to do this multi-processing stuff. So here it'll be an iterator over doc. Okay. What is Thinc? So Thinc is our machine learning library that does the machine learning operations. So let me just bring it up. I can either bring up the code, but I'll just bring up the docs page. So browser. I promise I'll get smoother at this before too long. Alright, so yeah, this has this system for like configuration and stuff, and then we can wrap things like PyTorch. So if you have something like a BERT model, what we do is we put this shim around it that has the PyTorch model instance, and then it means that this PyTorch model will have the same API as our native models, which are implemented directly in Thinc. So the component doesn't need to know that that either the whole network or just some part of the network is actually implemented in PyTorch. And in fact, the way that we use these things tends to be that we have a component of the model will be something like the BERT encoding or something like that. Will run in PyTorch, and then we'll add separate steps on with Thinc. So these are all of these layers, and let's see, where's like Where's the combinators? I think it's actually flatly in layers, which I always thought that maybe it would be a good way to put this out. But yeah. Okay. So I accidentally closed the window. All right. Anyway, I don't want to get too distracted with it. You can look at the docs and stuff. But long story short, we have our own machine learning library. It's called Thinc. All right. So transition. Right. Okay. So yeah. So yes, we want this pipe method. We would, that's definitely not a requirement that we would want to skip. I think it's nice to have that. Let's imagine that we don't want to do all of this multiprocessing because it's pretty difficult. This this linking with listeners, I'll come back to this in a second. This is the other thing that's super awkward with the way that the BERT models work in spaCy. And if nothing else, I think I've got a better idea of how to do this. So I'll get into this whole matter of how the listeners work, because it's always been evil, and it's a sort of known evil that I tried to come up with a better design for it, and I was never able to. But I think I have an idea for it now. All right, yeah, listeners, this is more of this evil that we're talking about. Yeah, the memory zones. So this is a new feature that I released recently to stop growing memory usage in spaCy. So what we do here is we have we let you declare a context manager, and outside of the context manager, any new vocab entries or string entries will be dumped. So having a context manager allows us to avoid the problem that we've otherwise had, where a doc might reference these lexeme or string objects that have been newly created, and we don't know when to free them up because we don't have a way to do reference counting feasibly to the objects in the docs. So instead of doing that, we let the programmer have responsibility for simply not accessing. We just declare accessing a doc that was created inside a memory zone, outside the memory zone, to be invalid. And then this allows this solution to this memory problem that we've always had. Now, if we're redesigning things to start with, I would try hard to not have a shared vocab and a shared string store. This was necessary at the time that spaCy was designed, or at least attractive at the time that spaCy was designed, especially because what you actually did for ML was access these numeric indicator properties. That's what most of what the ML actually was the feature extraction. And so having doing that sort of string to hash encoding and storing all of those features once in one place, and keeping those updated on the lexeme object and pre-computed at the lexeme object was a big win with this structure of model. But with now the considerations and everything, it's not at all clear that this is the way to go. So at least in this sandbox redesign, let's assume that we don't have something like this stored shared vocab or shared string store. And it may be that we find that, on balance, something like this actually is worth it. But let's try our designs and think through what it would look like if we didn't have this. Now, one thing I definitely would want to do is have things like this, the serialization. So let's imagine that we, still have the same to disk, from disk, etc. methods. Yeah. And just a tuple. Yeah. Okay. this isn't going to be quite right, but cool. We'll start with the bytes. All right. So let's review here. What have we actually got in our language? So this means that the pipeline, the only things that it has to do will be essentially just storing the lists of components, do basic manipulations over them, select subsets of them that you want, give you have control of returning them, adding them, and then it's also got a top level methods for serialization. So it's able to save and load the pipes, and even that actually might be something where that needs to be sort of reconsidered, because there'll be serialization methods that we want to call from PyTorch that might be higher level than what we have here. But for now, let's imagine that yes, within like a language object, you can do the serialization, and if there's some sort of global deserializer, that we'll just create an instance of it in PyTorch and do what we need to do. So that's the way that these individual components would work. That's the way that the pipeline would work. And what we would hope to do is give all of the components, their own sort of PyTorch model, and where that PyTorch model can potentially be part of a larger whole or reference a larger whole. And then from that, we're able to do the call into these training functions. So one of the cases that I think is especially interesting to think about this, so let's go to notes.txt. Okay, so So this means that, like, parser has a PyTorch model, etc. Okay. So let me just take a look. So there's, I just added some blank lines here. So there's, okay, right. Is that better? So now I've just added blank lines there. I'll resize the window in a second. But yeah, let me just look at the preview. Yeah, okay, cool. So yeah, thanks. That's good to know. That I've got to fix that. So yeah, the first situation that seems kind of simple is like, okay, every component has a 100% separate model. So in other words, if you've got like a tagger and a parser in your pipeline, you've got two PyTorch models, they have nothing to do with each other, there's no way to sort of run them together in a way that makes sense. We're going to have two calls into PyTorch that are just totally separate, and also for training, we'll end up with two calls that are totally separate. and importantly, output of tagger is not an input to the parser. So then a second situation is chain together. So this sort of situation doesn't come up so much with like, you know, a tagger and a parser, but as soon as you start getting like higher level components, like something like a relation extraction system or something like this, then indeed you actually end up, you know, wanting to have the named entity recognizer, you know, use recognized named entity tags as part of the relation extraction training. And this sort of thing was absolutely central in the pre-neural network days. You really had, like tagger features were crucial to parsing. Now this is, you know, really not the case because we have these word vector based approaches, and you know, there's not really a strong motivation for using something like, you know, part of speech tags as features in an entity recognizer or in a parser. You just you know, work from the word representations. And you know, this became doubly true when we had things like BERT, which were pre-trained, and now the vectors that you get out of BERT really have a latent representation of things like part of speech. There's, you know, very little motivation to have something like a part of speech tag. Entity tags, yeah, you can still end up wanting something like that because it means that the predictions of your subsequent models are aligned to your entity tags. You can also use the entities to do important pruning. So, for instance, in something like a coreference resolution system, you end up wanting to run the model over all pairs of entities. And so, if you can recognize entities as a pre-process, that, you know, has some motivation because then the set of things that you're recognizing over is like a much smaller set. As opposed to just taking, you know, the set of all, you know, phrases up to a certain length and using all of those as candidate entities. So, so what to do about this sort of thing? You know, how, because this type of situation is where we end up with this like pipeline logic intruding on training, and this is the sort of motivation that led me to want the language to own the training, to own the pipeline, because then you've got the pipeline responsible for going over the components, running them in turn, updating them in turn, knowing whether the components should apply during training and not apply during training. And importantly, the way that we do this in spaCy is actually a little bit trickier or unusual in that if you're training, say, a tagger and a parser together, as you're actually making the iterations on the tagger and you're making the iterations on the parser, the parser would get features from the tagger that reflect the current inaccurate model of the tagger. So it's seeing non-gold standard tags. And this again used to be something that was very important. And what you had to do previously, if you didn't do this sort of thing, was what was called jackknife training. You would train a different fold for each, you know, part of your corpus. So you would say have 10 different tagger models just so that you could apply the tagger on the held out fold, so that you could laboriously get tags which weren't perfect, that reflected the sort of errors that the parser would see from the tagger. Because if you didn't do this, then the parser learned to rely overly on the tagger decisions. And there was especially some categories which the tagger was, you know, not so sure about, like, you know, marking whether something was a phrasal verb or something like that, which was extremely telling for parsing. And so you would get accuracy that was notably worse if you trained on gold standard part of speech tags. So this was something which, you know, if you're just doing experiments, it's, you know, totally fine to say, all right, I'm just going to once compute this jackknife training and compute my, you know, my file that has runtime predicted tags, and I'll use that as my input to the training process. But when you're doing things, when you want to provide a sort of like unified training experience, the ability to do all of this in line was very attractive, and it made the training significantly simpler. The API was you give it, the examples, and then it's going to do all of these things. It's not going to require these separate passes and separate computations of this artifact and that artifact, etc. So yeah, just to answer the question in the chat, this is the next part of the next situation, because this is something which we do allow sort of at the moment with this awkward listener mechanism, and it's something which it's important to support at least in some capacity. So it's a requirement that I'll come to. It's like the situation 3. So I think in summary for situation 2, what we can do is actually, I would move this complexity outside of the library as well. And so if you have training situations where you need this sort of thing, you just have to run more things and compute a version of the corpus that has the runtime tags that you need. So we have in spaCy, the training process takes a pair of doc objects, the one that you're going to predict over, and the one which is the full gold standard, and you have the opportunity to produce that however you want. And so I think sacrificing the convenience of doing this chained together thing in order to take the logic away from the language class, I think is worth it. So yeah, okay, so here we go. Simple different PyTorch models. Okay, so avoid temptation to let spaCy handle this logic. So now we come to situation 3, and this is where we have shared layers, or where the models are entangled in a more interesting way than situation 2. In situation 2, the models are entangled at the level of the outputs. So this model produces some discrete outputs, it produces labels, and then the labels are inputs into the parser. And this means that we're never backpropagating errors from the parser to the tagger. But this isn't the only way to compose different parts. Instead, what we can have is composition at the network level. Models share components, share subnetworks. So tagger uses features. Uses contextual encoded vectors. Actually, let's just say transformer output from BERT. Parser uses same outputs, gradients from both. Okay, so this this requirement is already difficult in spaCy, and this is where we get to this listener mechanism. So here I'll explain how this currently works, and it's not pretty. and I think we can do better. But this is kind of the one of the key problems, or like how do we handle this sort of situation? And this sort of situation is extremely important because by no means do we want to have a separate transformer running for each pipeline component. That is just not a thing. There's some situations where you can do that and whatever, but the need to at least support having a shared transformer layer is crucial because otherwise the efficiency is just disappears, and we lose this thing that I was saying before, where we want to make use of these larger encoding models. This only works if you're going to run them once. If you're going to run it once per pipeline component, then it's a whole different situation. And it's also going to be very important. So a simple way to do this is you just say, well, you don't backpropagate. So you just essentially chain them together in the style that you do in situation 3. So you have a static but encoded model. You're going to run that during training time, and then that's going to produce these vectors, and then you're not going to backpropagate gradients to it. That is very limiting, and I haven't been able to get the same accuracy that I can get when I am allowing the components to backpropagate to the transformer. So I think especially if we're designing this from a sandbox, this requirement I think is important. We want to be able to do this. So we want to have some model that essentially attaches different heads to a transformer, if you want to think about it that way. So if you imagine it's sort of structured like this, where you have something like pre-process or tokenize, and then imagine this is this operator is like imagine this stands for training, and then we're going to pass that into the transformer. Then we're going to pass that into some set of different heads that we've concatenated together. So imagine you have something like a tag head, an NER head, and a parser head, and where this is one big vector that's being computed from it. Or you might have something that runs a little bit more flexibly, where you take where there's a part that takes like a cross product or something like this, and so it's not literally a vector concatenation, but it's still something that's just like attached to the other layer. And we'd like to have that structure represented to PyTorch, so that if you have this if you're able to define the model as the model for different components as one PyTorch network, then we should allow it to be optimized that way. So where if this sort of model structure is possible to do, then it's highly desirable to do it that way, because we're able to pass to PyTorch in one larger step, we're able to pass to optimizers in one larger step. So if you can do this sort of thing, we should. All right, so how do we do this at the moment? How do we pass gradients back from a model? So let's go back to spaCy. So let's say that's the right place to look. All right. So here we have a pipeline component that is called talk2vec. This thing's job is to apply a token to vector model. So it does some contextual encoding. As it happens, the default model architectures for this use a CNN, but it could equally use an LSTM, or you could in the same place use a transformer model. There happens to be a separate class called transformer listener, because we store extra stuff for transformer models, and we do some other things besides. That lives in the spaCy transformers library, or spaCy. There's another library as well. But it's simpler to think about this as just this. So, all right. At runtime, there's no problem. We set the information into the doc object. We say, hey, here's your tensor that represents your the contextual features, and then other components are going to read that because at training time you're not writing anything. So the question is, how do you get multiple pipeline components writing their gradients back to the same place? So what we do is we have this listener system, so this guy knows that so you're able to have these sort of parts of a model that are called listeners that register themselves here. And what the listener will do is actually ask, it has a reference to like its upstream, and so when it runs, it pretends to be a normal model layer. So from the perspective of the tagger or something, it just says, hey, here's a model layer that I can ask for contextual encoding, and the listeners, the way that it actually works is going to, call into our, it's going to call back to this talk to vec part and get, and then during the backward pass, we're going to pass the gradients back here as well. So, so yeah, here's how the update ends up looking. So we've got our set of examples. We're going to call our this begin update method from that we have in Thinc, where we get this callback. So we've got our token vectors and a callback that we need to call with the gradients. So after we get the gradients, however we get them, we call that callback with the gradients, and then that does the back propagation. So, so what do we do here? Well, we produce our own little wrapper callback where we've yeah, okay. So all of the listeners except the last one get this callback, and this callback is going to accumulate the gradients in one place. So this non-local D top effects, that's the gradient, and then we pass a different callback to the last listener, and that one is actually going to call the that sums up the gradients, and then it adds its gradient, and then it actually calls the back propagation of the parent model. So this is the call into the transformer, or in this case, CNN. So this is us saying, so yeah, this is the part where we're actually calling the CNN model, and we're getting its prediction, and we get its callback. Then we're going to do our operation, where our operation is telling all of these other listeners, like the tagger or parts or whatever that's registered to us, hey, run your thing, give us your gradient in your backward pass, and then the last thing that's listening, we're going to call its back propagation method. We're actually going to call our back propagation method, and then we're going to call the and then return this thing that's left over. So in other words, everything kind of works by having this sort of side channel. We go around the language class, and we have things just sort of registered like this. So I'll show you as well. Yeah, that appears okay, cool. So let's see, where's the actual listener? Yeah, here. So what do we do here? So this is a layer that gets fed its answers from an upstream connection, for instance, a component earlier in the pipeline, and then it's used as a sub-layer. So yeah, this is a subclass of Thinc.model. You're able to use this anywhere in a Thinc model that has the right signature. So anywhere that expects to to call into a layer that takes a batch of documents and produces a batch of vectors, you can use this guy instead. It can be used as a drop-in replacement for the actual CNN encoding or whatever. So and here's its here's where we do its forward pass, and where we're returning its the gradient from it. So what we do is we've got a kind of current. Yeah. So. Okay, so there's this. Right, so this sort of thing, these are the sort of fiddly details that we ended up having to deal with, because, you can end up in these states where you're trying to call the listener and the upstream component hasn't run over this batch of documents. For instance, you can, the whole thing collapses if you pass a different batching of the data to the talk-to-vec part, and then you're trying to batch the data differently when you're using the other, when you're using the listeners, because what you've cached in the talk-to-vec part, which it's supposed to provide to the listeners, doesn't match up with what you're actually going to try to the batch that you're going to try to run on. Yeah. Right, and then this is okay, so then we've got our outputs and then this empty backprop. So wait, I'm just reminding myself how this actually works. Receive. Okay. So yeah, we don't use the backprop callback of that function before, because we've got this like storing thing. So all of this is quite exceptional. It's not it's quite untidy, because, as I said, you have calls to a later object that appear independent from this previous object, but there's ways to call the two things together that are invalid, because there's this assumption that you're calling the subsequent components with the same batch of data that you called it with earlier. What this avoids is the need to have within the model objects the identity by reference. So we don't have one of the main obvious alternatives that you might try is saying, all right, well, we're just going to have this model and we're going to pass a reference to the same sublayer here and here. So with the current design, with the way that spaCy works, so one problem is you would just call into this function again, which isn't what you want. We would like to, cache the result and produce, so that you've only run the BERT or whatever once. We don't just want it to be the same weights. We want it to, sort of have this caching effect. And the other thing is that when you load back in, it's difficult to set up the same, object identities when you copy. It's difficult to set up the same object identities, that sort of stuff. So relying on object identity as part of this to say, all right, these two pieces of the pipeline have to have, this relationship where this object is the same as this other object. That's also, awkward, and it doesn't solve our caching problem. Although you could wrap a caching layer around the component or something like this, but then, when you add it all up, it's actually worse than the mechanism that we have here to listeners. So what should we do instead? Like, how should we actually do this? So I think that there should be some support at the language level for common components that, for just ML, where it's ML that's not attached to any pipeline component. And then you're able to, so you do that, you run that ML network, or you run that that ML part, and then the components ask the language object for access to those things. So there's some sort of more centralized prediction service, or prediction component, or prediction part, and you're going to, and the components need to know, or the models need to know that that they need to access that. So so this concept is still sort of only half thought out, but I think something like this should be possible to make something like this work. What gets difficult is allowing this sort of smooth drop-in replacement that we do allow at the moment. So the nice thing that we have going at the moment, which is nice, but something that if we have to sacrifice things, we have to sacrifice things. We have our tag class, and this just takes a model. The tagger itself does not know in any way how this model works. It just knows that its input is a batch of documents and its output is going to be a vector that has one sort of row per word. And then when we have different tagger models, so if we go to something like models tagger. So yeah, this builds the tagger model, and so when we build the tagger model, we take as a component of this layer top to vec, and that has to have the signature list doc and list floats 2D, and we're just going to use that sublayer. So when we're building the tagger model, we actually here as well don't know whether we're listening to an upstream component or whether we're actually running here our own encoding. So it's all drop-in like this. We produce our output layer, we chain them together, and then we return the model. And then we give the model a reference to its talk-to-vec layer. We're able to tell it, here's how to fetch your softmax layer, here's how to fetch your output layer, etc. So that's all kind of nice. But I think if we have to sacrifice that and make and sort of propagate upwards the logic that you're doing something different when you're calling into a shared layer than when you've got only your own layer, I think so be it. So this would mean that, as an example for something like this in the tagger, we would basically have an option here that's where you're going to ask it, or maybe it can be expressed on the model or something like this, where there's two versions. One version you're running directly from a batch of documents. Another version you're going to run from a set of vectors that represent these the contextual encoding. So basically, at the moment, this model has this signature, this doc, and then this floats 2D, I think it is, where each member of the list here represents the predictions for that doc. And what we'll have instead here is a union. So you could take that, or you can take list floats 2D, list floats 2D. So, and then if you've got this second situation, the tagger has to somehow receive the pre-computed vectors, and it has to somehow pass back its gradients after it's done with its part of the optimization. Or I guess actually in PyTorch you'd be passing the loss rather than the gradient. So this is again a sort of quirk of the way that I've done things in Thinc. We work on the gradients of the loss rather than the loss itself. Whereas in PyTorch and things, that first step of the optimization is done by the library. So here we're always working with the gradient, and the nice thing there is that, a layer doesn't know whether it's the middle of a network or the last bit of a network. If it's the middle of the network, it needs the gradient of the loss of the previous bit. If it's the end of the network, it needs the gradient of the loss of the objective function. So how would this look in, let's imagine that we wanted to do this with PyTorch. How would we do this? So I guess the question is whether we'd still be operating over batches of documents, right? Like we're not going to be computing a loss over all of it. So it's still going to be a matter of doing this. What we need to do is just have the component return the loss for that batch, and that means that realistically means running the forward pass first. So is there a way to do this even more? So let's go back to this composer framework and just look at what they expect us to do. If we wanted to use something like this, how do we make it maximally happy? So yeah, I'm just transitioning back. Wait. Yeah, so to answer the question in the chat, in the simplest case, you could concatenate the two PyTorch models. The thing is, there actually does end up being logic in the component about the loss, and that's something that I'm reluctant to give up. So, for instance, the tagger has this logic that if you've got missing values, if you're able to have some words where you don't know to tag, and those words don't count towards the loss. So that sort of thing is actually pretty. We won't be able to do enough NLP if we give up control of that sort of thing and expect that the loss can only be something like a categorical cross entropy over two things. We have to be able to do more flexible functions. And this becomes even more important if we want to have anything like the kinds of models that we have at the moment for the parser and tagger. This type, they work very custom because they do the structured prediction stuff. And we can, if we embrace PyTorch, we actually get access to doing those a bit differently, but we still want to have this ability to do the loss in a more custom way. So here, this is an example of okay, we've got this sequence categorical cross entropy, and then you're going to pass this your list of labels. It's normalizing, and then there's options like label smoothing and stuff like that. This sort of thing is all good, but we also want to be able to do things like check whether it's check for nuns and stuff. And actually, I think in our function here we have something like nuns, and here we even have in this function the ability to say that some word you don't know its full you don't know its tag, but you know it's not this tag, and we're able to optimize with that as well. So this is the sort of thing that I don't want to give up on. So we want that sort of flexibility too. All right. I switched back to the browser and sent the code. Anyway, let's go. So yeah, that would be so that would potentially be multiple gradient updates. But let's and that's the way that it works at the moment. Let's keep an open mind a little bit and think how this works. So let's go back to this mosaic and our composer. so let's look at its notebook and imagine what life would be like if we were using this. Okay, so here we've got, we've got loading our training and testing. This has to be in control of the batching and stuff. So, we have to be able to do that. And then we've got our model. We've got, and then this optimizer function here. So this, this just takes, a sequence of gradients and stuff. There's no reason why we need to be writing our own versions of that, although, we could if we want, but this is the sort of more low-level ML technology, which in practice of actually, we end up using quite custom stuff across our models, and we've experimented with custom optimizers and things like that, stuff that's not in PyTorch. But that's not an important requirement. I think, especially as we go to these BERT models and stuff, I don't want to have any particular opinion on optimizing them differently from other people, because it's so explored now. Whereas when I was doing this stuff before, there were few enough researchers that the experiments that I was doing were different enough that maybe there was an advantage to doing a different thing that nobody else was doing. But this is no longer the case. There's just such a density of work on this that I don't want to be doing some different optimizer from what other people have tested. All right, so here, and this is the learning schedule and stuff like that, and then we have to pass the whole thing over. All right, so this is, optimizing it as one model. So this does mean that, life is difficult if we want to compose different models in sort of these more tricky ways. We have to express it as like one PyTorch model if we want this to work. So we've got our training data and our testing data, and then if we want to do something like this labeling thing, that just has to be our, do we have a loss function? Like, what do we, surely, so this is decoupled SGDW, but where does it compute how does it compute the loss? Because it's one thing to say, okay, this is the optimizer, but that has to, that's taking, these losses and computing their gradient, but what computes the loss? There must be another option there that's, that you've just missed because it's, not, it's not something that a lot of people need to do. I mean, this is just a tutorial, of course. All right, let's see. Where did my chat window go? Lost my chat window, so. One moment.
Yeah, okay, there we are, cool. Right, okay. If it's, right, so now let's see what I missed. If it's multiple gradient updates, you probably want multiple optimizers. The gradient update / optimizer can only update parameters for a component if it's one of the component losses. I think that gets the updates that can train the specific components. Yeah, so what what I want to avoid is a situation where we've got, say, part of the network is the, to say it more simply, everywhere where there's like sort of a gradient flow needs to be one PyTorch model, because otherwise, because that's the only way that, you know, you can train it, because you need the gradients during training for the second model. We can't have some sort of thing where we've got one PyTorch model that does say the BERT part and another PyTorch model that does like the tagging part. That's what we do currently. So currently what we have is, you know, this ability to have them work separately. So if we go to Thinc, shims, so we got PyTorch shim. This is the wrapper that lives around you know, a PyTorch model and makes it pretend to be a Thinc model. So here we've got, you know, our inputs. We tell it we're in training mode. We tell it we get our output by running the model, and then because we're in training mode, the model has stored the ability to, it's stored the intermediate values that will be necessary for the backward pass. Then in this callback here, this is where we do, where we're actually going to do the backward pass. So here we get the gradients of the output, and this is where we convert all of this for PyTorch. So we, you know, and then we manually call torch.autograd.backward. So this is what we want to avoid. We don't want to be in this position of owning the loop that calls that sort of stuff, which means that logically it has to be one model. We can't have this, as long as there's gradient flow, that has to be one PyTorch model. We can have a separate PyTorch model if they've got, say, a parser or something. Yeah, right, so yeah, if we have something like, you know, let's say we've got something like this situation that we had here. So, where were we? All right, so yeah, we're in situation 3, and we've got models that share subnetworks. We have to have one parent model that it represents the tagger and the parser, and those are just like different outputs of the model. And then it has to have a custom evaluation function that where, you know, it's a custom you know, loss function that's going to get the gold standards for both the tagging and the parsing for a batch, and then it's going to compute the two gradients of those things. And you know, because it's like the two different outputs, and then you've we're able to handle that. So yeah, okay. Yeah. Yeah, so Adam, I'm not sure I quite follow. I suppose what you're saying is we could have different optimizers, like an optimizer that's only caring about you know, the updates to the parser, and an optimizer that only cares about the updates to the tagger. But my concern is they need to run within the same loop, because we can't do all of the updates to the tagger first and then the updates to the parser, because then we've trained, you know, the BERT model or whatever on the tagging task, and then we've next trained it on the parsing task, and so it might forget the tagging task. We want them to be a single objective, and that means that we have to be able to express it as a single PyTorch model.
All right. So, what's the API in this thing, and how can we? What will this actually look like? So yeah, we've got our model here. Functional API, auto micro batching. Where is loss? Is the loss owned by the model? How does this work? Maybe this is a PyTorch thing that I'm just being dense about that I haven't, because I haven't used it so much. But does the nn.module, does that own the loss? Blah, blah, blah. Composer.loss, here we are. A collection of custom loss functions and loss function related utilities. Okay, I mean, it's a pretty thin collection. People must need more than this. That's like, that ain't a thing. Okay, so where do we pass? So where do we pass this guy? Let's go to GitHub. Let's see if we can access the source. I see. So that makes sense if so long as these training loops are able to run multiple optimizers within the same loop, because they need to, on a single batch, each optimizer needs to run. What we can't have is one optimizer runs over everything and then the next optimizer runs over everything. All right, so let's see. I'll search within here for loss. I don't want issues. I want, commence. Us generating tokens for. Okay. All right. Let's go to our training. So this class looks likely. Does the browser show up okay? Yeah, that looks fine. Okay. Actually, is the code too small? I can zoom in a little bit if necessary. Oh yeah, this is sort of question as well, whether the training loss is accumulated over the number of tokens in a batch rather than the number of samples. So this is another thing that makes using general APIs really awkward sometimes, because the actual unit of loss in our models doesn't necessarily correspond so simply to the items in a batch. So for instance, here in this sort of thing, you've got a batch of documents, and then you've got the tokens within those things, and the model actually runs over each token. In the parser, it's actually a state machine, and the model applies over each state that we generate from during parsing. And that's the unit of loss. And then you can have a different parser model where it's a global model, and it predicts probability distributions over all of the states in the sequence, and then the objects to optimize over are actually the whole sequence. So it can vary. And then when you have things like co-reference resolution and other models like this, the mapping between the input objects and the actual items of prediction is complicated. Okay, so I must be missing something about this, because I really don't see where you specified a loss function here. Is it just as simple as you do that in PyTorch? It must be. So, oh no, I don't want this. Okay, so where's... Alright, well, I mean, it's the sort of thing where yeah, okay, so it is separate. So, right, okay, yeah, that's, I thought I was going insane there for a second. Alright, so that makes a lot of sense. So how do you specify the loss in this thing? These algorithms. I wonder whether Claude knows compose. Yeah, of course, this is a bit specific. No, this is nonsense. Yeah, it's just interpolated from my previous question. Alright, that's fine. I mean, maybe that's the answer, but there's, it could just as easily be nothing, so that doesn't answer any question. Alright, so that's on PyTorch now. Here's the loss. Yeah. Okay, so here we've got a loss. So here's the training loop. can't I see where this variable's defined? What's the shortcut to open this in oh, dot, that's what I thought. Why is this not? So I should check that I'm at the current version of this. Okay, so dot. Why does it not work? Must be at a different view. I don't know why that doesn't work, but usually it does. Yeah, so the question of like, why do I prefer PyTorch? I think the critical mass is massive, to the point that other things are, in my opinion, almost dead. So there's some niches where I think people are using JAX, but it's definitely more awkward than PyTorch for our situation. Anything where you have to, the more you have to define the graph up front and the less you get to sort of be in the loop, the harder it is for us to use the library for our stuff. And PyTorch, now it has more graph pre-compilation stuff with ON and X and things, but there's still a better level of access. And when I tried to use JAX, it was really difficult because I ended up needing to go back and forth from JAX too much. This was a while ago though. But whenever a new thing like Bird is released or whatever, it's going to be in PyTorch. And I do believe that PyTorch has better performance for these things. I don't think that there's any viable alternatives. TensorFlow I think has always been a mess, and it had the sort of first mover disadvantage of being saddled with its earliest conception and early design decisions, and then the iteration of changes that they laid over it, I think made things much more confusing and worse. So there's like 10 different, there's all of these different subsystems within a TensorFlow, and something that you're using might work one way and not the other. So I don't see this as attractive. And then there are other frameworks like I know that I think Paddle is still being used. I actually evaluated this ages ago, and I was quite impressed, but it's I still don't see it as like a big advantage over PyTorch. And at the time the docs in English weren't so good, the community participation in English wasn't so good. I just think that the advantage of using what everybody else is using is way too strong. And almost any user of spaCy will want it to be PyTorch. They'll want to, PyTorch will be the library that they'll want us to be using. So I think, I'm not bothering to take this to the community, but if I did, the response would be overwhelming. Overwhelmingly, people would vote for PyTorch. Okay, so self.originalModel.loss. So maybe you do call it, call into the model.loss. Claude, maybe I was too mean to Claude. He did not lie to me after all. Alright, so yeah, we get to define a loss function over the outputs and the batch, which is good enough for me. So yeah, we've got this loss, and then we And then PyTorch knows what this means. So then for loss in ensure tuple self.state.loss. And then, yeah, okay. All right. So yeah, what does all of this add up to? So we're gonna like the alternative to doing it this way would be to have like sort of one God component, like, you know, so if you have the identity of one component per model, what you can do is have a sort of component wrapper or something like this and say, okay, we've got a component that does the tagging, parsing, etc. This means that you have like these sort of nesting, and you have a pipeline where you're not actually able to iterate over the components, or you've got to sort of go down this component tree. I don't see this as very good. Instead, what we end up with is this sort of separation of the models from the components. So a component doesn't necessarily own its whole model, and in this sort of case where we've got like this extreme single modeling, then you have well, I guess everything end up kind of like this, because you know, if everything needs a BERT model, then everything ends up looking this way. And most pipelines end up, you know, with one model. You could, in theory, have pipelines with multiple models, but a lot of the time you'll end up with just one. So the question is how to make this convenient. Like, how do we make some sort of extensible model class that allows us to add heads and things to it, so that as you're adding components to the pipeline, you're able to do this? Because we could, you know, the most naive thing of just saying, all right, you write a whole pipeline and you write it together and then you write the model for it. This works, and it would satisfy the sort of the basic use case in spaCy of like, okay, we can, you know, I can go and produce a model like that everybody else can use. But we're losing the ability to have this, like, you know, for the pipeline to work the way that it does, where you can add another component to the pipeline, or, you know, and that sort of stuff. We can add rule-based components, but if you're adding any ML component, then it's not going to work the same way. So how do we make some sort of model class that's editable like this? So I guess yeah, let's just have the problem here. So
All right, I've got one idea. I wonder whether this ends up looking like the listeners again, but let's see. Let's go back here. Okay, so yeah, what if we had something like this, where you've got like class, you know, BERT proxy or something like this, or BERT reference, or dummy BERT. Or I don't know, shared transformer. Right, and then, yeah, it's the yeah, torch.nn model. Okay, so actually, we want this to be us. Yeah, fun times. Anyway, so my idea is that you write out the model for your tagger or parser or whatever, and in it you've got some module, some part of the network that stands in for where your extra stuff will attach to the transformer. So then when you add this to the pipeline, we go over the model, we find the parts where we attach here, and we edit, and we take, like, we graft these layers onto our common model. So that the pipeline is responsible for assembling the parent model out of the parts that that is specified on the components. So yeah, if it works that way, this is, you know, exactly as expressive as the listening mechanism that we currently have. So there's nothing that we can do now that we couldn't do that way, because it allows the same architecture of, you know, feeding forward to multiple places that are going to use the predictions and backpropagate to the same place. So this would work. We could, you know, use this, yeah.
I always underestimate how long it takes to actually install all of this. So this is the other thing that's made us, just sort of, wary of depending on PyTorch, or that we've seen as a disadvantage of it, that it's such a massive dependency. You end up throwing in so much stuff. And in fairness, the equivalent stack that we have in spaCy, if you use the GPU library and stuff, it's not small either. You have QPy, and it does end up pretty big, but this is still a lot bigger. And so I wonder whether there's too many users where this is so unattractive that you've got to, if you just want to do some rule-based matching and stuff, and you got to load PyTorch. So if we do this, what we're going to have to do is have the pipelines separate as a dependency from spaCy. So we have to have a spaCy core that consists of the language, the vocab, the token, the doc data structures, these sorts of things, that doesn't have any ML dependency. And then different pipelines can do their ML, can bring in their own ML stack. And ideally we're able to have a pipeline that that works via PyTorch, and then a pipeline that works via Thinc or something else, so that if we want to maintain the current sort of trade-off that we have between the installation size and the more complexity that we can. The other side of this is, well, look, if a large enough fraction of people are just using PyTorch anyway, this cost is paid up front. And so if everybody's ML environment starts out initialized with PyTorch, then this isn't actually a cost. This is just whatever. It's common. It's already paid, and we may as well use it. And in that sort of situation, we're actually making things harder by introducing new things that are to download. Like QPy and stuff, even if they're smaller overall, well, they're not smaller than the one you already have. So it's the trade-off is tricky. It's a bummer to download over a gig of stuff, but just how bad is it? If it makes life easier, and if it's kind of the way forward, then maybe we should just embrace it. All right. All right. So yeah, let's see what we have in this bubble scratch. So here we've got our shared transformer, which would be a model subclass, and this would be Okay, all right, so I think this is, the solution here still feels unideal, this stuff about, traversing the tree and getting in and replacing stuff. This is a bit, it doesn't feel as fantastic. I guess you could do something with strict object identity where you just where when you're composing something like Tagger, you pass in the transformer instance. But I think it's going to be so sort of awkward that you have to create the transformer model separately and then pass it forward. I think being able to instantiate the objects by themselves, I think will be quite nice. So yeah. All right, I'm going to leave it here and come back to this next week after giving this some more thought. So the plan would be to march forward with this sandbox and get something working that trains like two components, probably a tagger and a text classifier, in this sort of separable way, so that we can understand how this actually works end to end. Then the next step would be thinking through in more detail how something as complicated as a parser would work. And there, I wouldn't use the parsing algorithm that we use in spaCy at the moment. I would use the by-affine parser. I'm sure most people don't know what this is referring to. It's like, parsing literature, but basically there's one which does sort of everything at once, like it computes the probabilities that each pair of words are attached to each other all in one go. This is much nicer on GPU. It does have the problem that the downside that it's quadratic in the length of the sentence. So it means that we can't process whole documents the way that we do in spaCy. However, I think if we're going to be relying on something like BERT, then BERT has a fixed window, so we're not actually gaining anything by having this sort of next parser step that's able to iterate over the tokens. If you're going to operate over slices of the data, we may as well just, we may as well have something like a sentence and have a parser that runs over sentences. So I've been interested in switching over to by-affine parser for quite a while. I think that it's this style of parser is more flexible. It bakes in fewer assumptions about the specific ML problem, so that we're likely to get better performance and NER and things on sort of a different class of problems that don't behave exactly the same way as the NER things that we're trained for. And on GPU it'll be a lot faster. On CPU it'll be slower. If we're thinking about a pipeline that's like GPU optimized or GPU native, I think that having the by-affine parsers are, definitely a good model to have as a default, or to have in there. So yeah, cool. All right, see you all.